So, in the last lecture, we have discussed several tests for judging the absolute convergence of the series of real numbers, and those sets mainly we have discussed the nth root test, comparison test, ratio test, integral tests. Now, even we see that these tests are good enough to judge the series to be convergent, absolutely convergent or not, but still there is a case of failure. When the limit of x n to the power 1 by n, limit of x mod x n to the power 1 by n as n tends to infinity, if this limit comes out to be 1, or limit and similarly, and limit of this mod x n plus 1 over x n ratio test as n tends to 1 comes out to be 1, then both both nth root test and ratio test fails. Root test and ratio test fails. We are unable to decide whether the given series is absolutely convergent or divergent, or it may be convergent, may be divergent depending on this. So, a further test which will help in this direction is given by Ravi, which is known as the Ravi's test, and that can be applied only when we see that this test fails. We can also, but initially when we start with that, we always consider step by step, go step by step, and then if required, then we come for the higher order, higher level tests. So, Ravi's test says that is, let x, which is x n, be a sequence of non-zero real number, be a sequence of non-zero real numbers. Now, first part, if there exist numbers a which is greater than 1 and k which belongs to n, the set of natural number, k is a positive integer, k get such that mod of x n plus 1 divided by x n under mod is less than equal to 1 minus a by n for all n greater than equal to k. Then the Ravi's test says the series sigma x n is 1 to infinity converges, is absolutely convergent. Now, on the other hand, if there exist real number, numbers a which are less than or equal to 1 and k is a positive integer such that mod of x n plus 1 divided by x n under mod, if it is greater than equal to 1 minus a by n for all n greater than equal to k, then the series sigma x n 1 to infinity is not absolutely convergent. It means it will be a diverging series, absolutely convergent. The proof of this follows as it is. Suppose, let us give this number, suppose this is inequality 1, this is 2. Suppose 1 holds. Then we have to show the series is absolutely convergent. So, 1 holds means mod of x n plus 1 by x n is less than equal to 1 minus a by n. There exists a number a greater than 1 such that this is true for all n greater than equal to k. So, let us replace n by k, small k suppose. Then what we get is here that k into replace n by small k. It's nothing, no problem, it's replace n, and then we multiply this. So, k into mod x k plus 1 minus less than equal to k minus 1 into mod x k minus a minus 1 mod x k. This is true for all k greater than equal to capital K. What I did is I just used this in place of n, let us say small k. So, when you multiply by this k, you are getting a k times mod x k plus 1 is less than equal to 1 minus a into mod x n. This can be manipulated like this. It can be written as k minus 1 mod x k minus this, because mod x k gets cancelled from here, and basically you are getting this k minus a into mod x k. Okay. So, this way we are doing. Now, again reorganize it. So, this implies that k minus 1 into mod x k minus k times of mod x k plus 1. This term is greater than equal to a minus 1 into mod x k, and this is true for all k greater than equal to capital K. Now, a is strictly greater than 1 in the case 1, first case. So, a is greater, so this is a positive quantity. This is also a positive quantity because we are choosing x n as a sequence of the non-zero real number. So, mod of x k will be positive quantity. So, what it shows? This shows that k times of mod x k plus 1 basically is what is a decreasing sequence. So, what we get is, so this implies that the sequence k into mod x k plus 1 x k plus 1, this sequence is a decreasing sequence of real numbers for k greater than equal to capital K. Okay. Now, if I add this one, let it be this quantity k minus 1, let it be 3, this third. Okay. Now, if we add this from use 3 and add for small k is capital K plus 1 up to say n. So, when you add, this will automatically telescopically few term will get cancelled, and finally, we get capital K minus 1 into mod of x capital K minus n mod of x n plus 1 is greater than equal to a minus 1 into mod of x capital K plus mod of x n. Okay. Now, since a is greater than 1, so a minus 1 is non-zero. So, a minus 1 is different from 0. We can divide by this. So, this implies that mod of x capital K plus up to mod x n, then plus n by mod x n plus 1, n times mod x n plus 1 divided by a minus 1 divided by this a minus 1, this a minus 1, this term you are taking here, okay, and divide by a minus 1 is less than equal to capital K minus 1 divided by A minus 1 mod of x k. K. Okay. Now, k is any numbers, is it not? So, k minus is a fixed number, k is also fixed. So, this is basically a finite quantity, this is finite, okay, bounded. Now, here if I look this one, n is greater than mod a minus 1, because once a is fixed, then n can be taken so large, so that n over a minus 1 is greater than 1. So, basically this entire thing is greater than the series sigma mod x I is capital K to n plus 1 is greater than this. So, what they show that this series, when n is sufficiently large, this is bounded series. So, this implies that the series sigma mod x n, this series is a bounded partial sum of this series, partial sum of the series this is bounded. Okay. So, partial sum of this series is bounded 1 to infinity, and the series and the terms of this series k into x minus is a decreasing sequence of real numbers, is it not? So, this is a bounded sequence and monotonically decreasing sequence of real number, because once it is decreasing, mod x k minus 1 will also be k times. Okay. So, this is a bounded sequence, hence every bounded sequence is a convergent one, monotonic. Okay. So, this shows that the sequence, this implies the series x n 1 to infinity converges absolutely. Absolutely. So, this is the proof for this part 1, this is part A. Proof for part B. Now, in this case, it's we given that this relation given that there exist real numbers a less than or equal to 1 and k a positive integer such that mod of x n plus 1 y x n is greater than equal to 1 minus a by n for all n greater than equal to k. So, what this show? This shows that if we multiply this n into mod x n plus 1, this is greater than equal to n minus a into mod x n minus a into mod x n. But what is? But a is less than equal to 1. So, minus a is greater than equal to minus 1. So, it is greater than equal to n minus 1 mod of x n, as a is less than equal to 1. So, n of mod x n is greater than, this implies the sequence n into mod x n plus 1. This sequence is an increasing sequence. Increasing sequence of real numbers for all n greater than equal to capital K, for all n greater than equal to capital K. So, once it is increasing, so if we take any c, then n can be obtained so that it is greater than equal to c. So, and there will exist a number c. So, there exists a number c greater than 0 such that this mod x n plus 1 is greater than c by n. Okay. And this is true for all n greater than equal to capital K. Therefore, the sigma of this x I is n plus 1 to say infinity is greater than c times sigma of 1 by I is n plus n to infinity. Now, this is a harmonic series. This is a harmonic series. So, what we do is that if I take I equal to 1 to infinity, that is sigma I is equal to 1 to infinity mod of x I is greater than equal to say same terms we are adding here. So, sum C replaced by C dash is greater than equal to sigma 1 to infinity 1 by I, is it not? Some few terms we are adding here. So, that can be written as a some C dash sign or maybe plus something, but this is a harmonic series, harmonic series. So, once it is harmonic, it means it will be a diverging one. So, diverges. So, once it is diverges, this series will be diverging one. So, this implies that series sigma mod x n is 1 to infinity is not absolutely convergent, is not convergent. Therefore, original series will not converge absolutely. So, that is the reason for this. Okay. Now, the equivalent as a corollary of this, because it is difficult to get this ratio. So, in terms of the limit, we can easily get this test which is applicable, and so as a corollary we can say let x which is x n be a non-zero sequence in R, set of real number, and let A is the limit of this, limit of n 1 minus mod x n plus 1 by x n mod of this as n tends to infinity, suppose A, whenever this limit exists. Okay. So, this then this series sigma x n 1 to infinity, this is absolutely convergent, when A is greater than 1 and is not absolutely convergent when A is strictly less than 1. For A equal to 1, again test fails, we are unable to get. So, we have to apply some other tricks for that. Okay. A is less than 1. The proof runs as usual. Suppose the limit in this, let it be this 3. Suppose third exists, limit exists in 3. So, it means the limit of this is A, where A is strictly greater than 1. So, we can identify. So, there exists. So, if A 1 is a number, A 1 is such which lies between A 1 is less than A 1 less than A. For this A 1, there exists some k, a positive integer k, such that A 1 is less than n times of 1 minus mod x n plus 1 by x n for all n greater than capital K. This is because this limit is A, okay, and A is strictly greater than 1. So, if I choose a number in between 1 and A, it means there will be a sequence of the term of this series which will exceed by A 1, then only the limit will go to A. Okay. There are the sequence, because limiting is going to A. This is 1, here is A, the limit is going tending to this. So, what I am doing is I am choosing one A 1 here. Okay. So, an n can be obtained, a k can be obtained such that when you take all n greater than k, all the terms of the sequence will fall here, that is they are greater than A 1. So, if it is so, then what happens to that? Therefore, this series when this converges. So, we get from here that therefore, this implies what n plus x n plus 1 over x n. This will be, when you transfer it, what you are getting is less than 1 minus a 1 by n. Okay. But a 1 is what? And this is true for all n greater than k, but a 1 is strictly greater than 1. So, by Ravi's test, since a 1 is strictly greater than 1, so by Ravi's test, the series sigma x n 1 to infinity converges absolutely. Similarly, for the other, if a is less than 1, the result follows. In a similar way, you can prove that this result is true. Okay. Now, we have seen the corollary and the result. Now, this corollary is weaker, basically the result is very strong, that is, this ratio, this type of thing is stronger than this one, which can be seen easily by the following example. Suppose I take this problem, let us consider the series sigma n over n square plus 1. Test for the convergence, absolute convergence, all the terms are positive, test for the convergence of this series. Now, if we apply the results here, suppose I take here the x n is n over n square plus 1. So, x n plus 1 becomes n plus 1 whole square plus 1. So, when you take the x n plus 1 by x n mod of this, then what happens to the x n plus 1 over here, this comes out to be what, n plus 1 by n, this term, and then n square plus 1, n plus 1 whole square plus 1, and then limit of this as n tends to infinity, limit of this as n tends to infinity. Now, limit of this is 1, again when you divide by n square, the limit will come out to be what, this is 1, and then this limit x n plus 1 by x n plus 1 by x n n over n plus 1, it is 1 or not. Let us see, n square plus 1, so 1, then 1 and plus 1 2. So, why it is n plus 1, calculation limit of this is x n is n over n plus 1. So, if you take this n plus 1, n plus 1, n plus 1. So, divide by n plus 1 square, okay. Divide by n plus 1. So, we get from here is n plus 1 square. So, what we are getting is 1. Divide by this n plus 1 square. This is, sorry, that is why it is a mistake. This is n plus 1, not n. Okay. So, divide by n plus 1 square here. So, this limit is 1, this limit is 1, product will be 1. So, the ratio test fails. Now, if I take the Ravi's test n into corollaries of the Ravi minus x n plus 1 over x n, this thing, and then take the limit of this as n tends to infinity, then again you will see this limit comes out to be 1. Okay. We can just solve it and get this, we get the limit to be 1. So, again fails. Okay. We are unable to do that, but this is by corollary. But if we look the x n plus 1 by x n, what you are getting? X n plus 1 by x n, this is nothing but what is greater than or equal to n minus 1 by n, is greater than equal to n minus 1 by n. If you just see the ratio of this and find out the term, you will get this is greater than equal to, that is 1 minus 1 by n. Okay. And this is positive 1. So, this diverges. So, by Ravi's test, the series sigma x n does not converge absolutely. So, this shows that though the Ravi stage is difficult to find out these type of ratios and get the decision, but it is much stronger than the corollaries of this Ravi test. Okay. So, but practical the corollary is much more easy to apply rather than to this. Okay. So, that is what. So, this is all about this convergence or absolute convergence of the series. Now, we will switch over to limit of functions. Okay. So, next topic you say limit of functions. First, what is the idea of this? Suppose f is a real valued function. Let f is a real valued function, that is f x when x belongs to R is a, and f x is also real. When we say the limit of this f x when x tends to a some number c, where c is any real number, say R, where the okay. When we say the limit of this is L, the meaning of this is that if this is function f x, I am assuming to be continuous function of course, and this is our c, c, and x is a point which converges to c, then correspondingly the functional values f of x is tending to L, When x approaches to c, the limiting value of this f x is L. At the point c, the function may or may not be defined, but still the limiting value of this f x we say it is L. It means the difference between L and f x is very small when x is sufficiently close to c. It means that is the f x is close to L when x is sufficiently close to c. That is the meaning of the limiting behavior of the function f x at the point c. At the point c, the function at c, the function f x may or may not be defined. It is not necessarily defined, but what is used important part is what it is necessary that the point, the necessary part is that f should be defined, at points near to c. Then only limit of the f x has some meaning. If the function is not defined at the point closer to c, then we cannot approach the value of f x when x is approaching to c, because there are so many points where the function is not defined, we cannot find out the f x. So, the important part or necessary part is that in order to get the limit of the function at a point c, the necessary condition is or necessary part is the function must be defined at all points which is very close to c. That is the important point. Second point which we get, that at the point c, the function the c may or may not be available in the set A, still we can find the limiting value of f x when x approaches to c. Suppose I say the function f x, say f x is defined over the interval say 0 to 1, and we find the limit of the f x when x tends to 0. So, though the function is not defined at the the 0 point is not available in the set A, but still this has a meaning, because the function is defined at every point in the interval 0. So, what it says is the point c may or may not be point of A, but even if A the limiting of the f x is possible. We can ignore that point, that whether it is in C or not. What we are interested in, that we will find out the neighborhood of the point A, neighborhood of the 0, this is the 0, we will find the neighborhood of the 0 with a suitable radius delta, and then find the intersection with A. In this, all the point in this set, consider the functional value at this point and take the limit when x approaches to 0. If this limit exists and equal to L, we will say the limit of the function exists. Okay. So, that is what. So, note we can write it note like this. The point C, okay, may or may not be in the point C may or may not be in the set, but still the limit of f x when x tends to C can be defined provided x tends to provided x belongs to the neighborhood of C intersection A. Okay. Function is defined for this. Okay. So, that is the problem. So, before going for this limit, let us see the concept of the crystal point, because always this limiting value that we will consider C as a crystal point for this set. Okay. So, let us see the definition. Cluster point, of a set A. Let A be a non-empty subset of R, a point C, a real number in R, is said to be a cluster point C, said to be a cluster point of A if for every epsilon every delta greater than 0, there exists at least one point x belongs to A, which is different from C, such that mod of x minus C is less than delta. Okay. So, what is the meaning is that a point C is called the crystal point of a set A if for every delta greater than 0, there exists at least one point x such that x minus C is less than delta where x is. So, this meaning is x minus C mod of this less than delta obviously means that x lies between C minus delta and C plus delta. It means there exists a neighborhood around the point C. It is a neighborhood, this we denoted by V delta C, a neighborhood which is C minus delta C plus delta. Okay. So, a neighborhood can be obtained this in which at least there exists one point x different from C and this is true always for each delta. Okay. Then we say C is the limit. So, C is the crystal point of the set A if when we picked up the neighborhood of delta, then at least one point x will belongs to this different from C. In other words, you can say a point, or we can also define in terms of the neighborhood, a point C is a cluster point cluster point is also called the limit point. Okay, is cluster point or maybe the limit point of a set. Cluster point of the set A, of the set A, if every delta neighborhood, if every delta neighborhood, NBD neighborhood, every delta neighborhood, NEIGH neighborhood, NBD, we will use the word NBD, neighborhood B delta C, that is C minus delta, C plus delta, every neighborhood of this of C contains every neighborhood contains at least one point, of A distinct from C. Okay. Then we say C is the cluster point of this. Okay. So, basically this is our suppose set A, C will be somewhere here. Now, this will be the cluster point. If we picked up a neighborhood around the P, then there must be a some point x of A different from C available, whatever however small radius you choose. Then we say C is the cluster point. The point C may or may not belongs to A. So, that is the important part is C may or may not belong, may not be a member of A. If it is in the set A, then also we can ignore it. Then even if it is a member of X, it is in A, but still we can ignore it. Then still we ignore it while deciding the cluster point, by deciding C as a cluster point. What is more important is that be picked up, be simply picked up whether it is a cluster point or not. Okay. What we see here, we require, that is because we need to show that there is or there be a point, in the delta neighborhood of C intersection A. That is important part, distinct from C, in order for C to be a cluster point. Cluster point of A, that is important. For example, suppose I say A is a set having two element 1, 2, then 1 is not a cluster point. Obviously, 1 is not the cluster point. Why? Cluster point of A, because what we see, if I take the neighborhood of 1 with central set half with radius half and find out the intersection with A, then this set contains only the single point 1. So, there is no other point. So, there does not exist x which is different from 1 in this set, in this collection V 1/2 1 intersection A. Hence, 1 cannot be cluster point. Similarly, 2 cannot be crystal point of this. Okay. So, this way we can identify for them. Okay. Now, there is a relation, and we can also define the crystal point in terms of the sequences. So, this result is which connects the concept of the convergence of the sequence and this crystal point. A number C belongs to R is a crystal point of a subset crystal point or limit point, same, okay, limit point of a set, crystal point of a subset A of R, if and only if there exists a sequence A n in capital A such that limit of A n as n tends to infinity is C and A n's are different from C for all n belongs to capital N set of natural number. So, that is the important part is. Okay. Proof of this is, it means if C is a crystal point of a subset A of R, then there will be a sequence available in A. If this is our C and here is A, so there will be a sequence x 1 or A1 A2 n, A1 A2 n and so on, which will converge to C, which will go to C, but A's will be different from C. That is, if I draw a neighborhood around the point C, then you will get the A's different from C. For any neighborhood, we will get at least one A's available in this. So, let us see the proof. If C is a crystal point of A, then by definition, if it is then by any delta neighborhood of C must includes the some point which is different from C. So, delta I am choosing to be n, then for 1 by n, then for any n belongs to n, the 1 by n delta neighborhood of C, the 1 by n neighborhood of C, delta becomes 1 by n, contains at least one point A n which is distinct in A n in A, distinct from C. This is by definition of the crystal point. So, what we get? Then we get A n's, these are in A n's are different from C, and the distance of A n minus C is less than 1 by n, and this is true for each n. There will be some A n's. So, this implies the limit of A n as n tends to infinity is C. Okay. Conversely, if suppose the limit of A n is given to be C, given that limit of A n's as n tends to infinity is C, means there exists sequence A n such that limit is n. Okay. So, conversely, given a sequence A n, in the set A minus this C, such that limit of this A n is C, this is given. So, by definition of the limit, then for any delta greater than 0, there exists a k, a positive integer k, such that if n is greater than or equal to k, then A n's will belongs to the neighborhood of C with delta neighborhood of C. That is by definition of this. Okay, for any delta we can find out this. There after certain stage all the terms of the sequence will belongs to this delta neighborhood C. Therefore, delta neighborhood, therefore, the V delta C, delta neighborhood of C contains the point n's for all n greater than C and different from which belongs to A and distinct from C, distinct from C. So, this implies that C is the cluster point of A, is it not? So, C is the cluster point of A. That's one. It means we can, in terms of the sequence also, we can define the cluster point, okay, in neighborhood or cluster. Now, let us see few example. Suppose x I take open interval or A with the open interval 0 1, which is subset of R. Okay, R. Now, this is a complete interval 0 to 1. Every point will be the cluster point. Why? Because when you take any point here C, any point of this, say I take C here, then one can identify any neighborhood around the point delta neighborhood if I choose. Then one can identify the points of the set which is distinct from C. So, C becomes the cluster point. So, and this is true for any C is arbitrary in between 0 1. So, every point in the this is a cluster point, as well as, so every point including 0 and 1 are cluster point. 0 1 is also cluster point for this cluster point, but neither 0 and 1 both are not available in A. So, similarly, closed interval 0 1 we can choose like this, say finite set of real numbers. Then finite set of real number means suppose A 1, A 2, A n, these are the sets, elements of the set, but it does not fit at any limit point, has no cluster point. Why cluster point? Because if suppose some point is a cluster point, say any point whether in between or outside. If suppose say A 2 is the cluster point, then there is a gap between A 2 and A 1, A 2 and A 3. So, if you draw a neighborhood around the point A 2, you will not get a point other than A 2 inside this. Basically, no point will be available. So, it cannot be a cluster point. If a point is outside of this set, again there is a gap between A n and this, and we cannot get the a point in the neighborhood delta which is distinct from this. Okay. So, point of the set. So, this is not a cluster. So, finite set does not have a limit point, no cluster point. Similarly, infinite set capital N of natural number has no cluster point. The same reason is the same, because this is our natural number 1, 2, 3 and so on. Now, we cannot take get any neighborhood around the point which contains the point other of the set other than that point. Suppose I take 1 and I say 1 is the cluster point, say, then if I draw a neighborhood like this, now this neighborhood does not contain a point of the set other than 1, because basically no point is available. So, 1 cannot be a cluster point. Similarly, 2, 3 are. So, this infinite set and has no cluster point. Then fourth example, the set A n, if I take the set 1 by n, where n is a natural number. Now, this has 0 as a cluster point. Why? Because this is our 0, here is 1, then half, 1/3 and like this. So, the sequence is decreasing, okay, decreasing and it clustered around the point 0, means if I draw any neighborhood around the point 0, there are so many points will be available here after a certain stage, which are close to 0 and different from 0. So, 0 becomes the cluster point for it. Then if we take the I, an interval closed interval 0 1 and consider a set A which is I cross intersection Q. Q is the set of rational numbers. It means the interval 0 1 is chosen, and then from there you are finding the intersection with Q. So, A is the set of all rational numbers lying in between 0 1, this closed set 0 1. Okay. Then every point in I is a cluster point of A phi. Then every point I, then we claim then every point of I is the cluster point of this set A. Every point in I or I is a cluster point of this. Why? This is because of the result which we have seen, that between any two rational number there are always a rational number. Infinite rational number can be finite in between the two rational number. So, if I picked up any point here say 0, then draw the neighborhood. Now, since between 0 and 1 rational numbers are dense, this is the reason is because rationals are dense in real. Closure of rational number is the entire real line. Okay. So, once it is rational dense, so if you picked up any number, you will always get in vicinity another rational number, and which is distinct from that number. So, every point of 0 1 becomes the closed cluster point for this set A. Okay. So, that is one. Now, we come to the concept of the functions crystal. Now, this important part, definition of limit. Let A or limit of the function. That is important. Let A be a subset of non-entry subset of R, and let C be a cluster point of A. For a function f, which is a function from A to R, a real number capital L is said to be a limit of the function said to be a limit of f at C if given any epsilon greater than 0, there exists a delta which depends on epsilon, of course, delta depends on and positive. There exists a delta greater than 0 such that if x belongs to A and 0 less than mod x less c less than delta, then mod of f x minus L is less than epsilon. That is what is okay. So, what is the meaning of this is that A x this is our C is the cluster point, C is the cluster point of a set. Suppose this is the set A, okay, and C is a cluster point for this set A. A function f is defined from A to R. So, this is our function f, which is defined carrying A to R. This is R, suppose here everywhere the function is defined. So, we get this is f x range of this. So, what he says is that if we say that L, this L is the limit of the function f x at the point c, that is if I take x and x tends to c, the corresponding function f x, this goes to L, limit of f x is L, means that if we take any epsilon greater than 0, then there exists a delta such that this for all x belongs to this and f x minus L is less than epsilon. So, if I take a epsilon neighborhood around the point L, that is here f x minus epsilon, f x plus epsilon, if we choose this, that is this is our f x minus epsilon, f x plus epsilon. Here is c, c minus delta, c plus delta. So, for the given epsilon greater than 0, for the given epsilon greater than 0, there exists a delta such that whenever we take any point x different from c in this neighborhood, the image of this will fall within this range, within the L minus epsilon to L plus, sorry, this is L minus epsilon, L plus epsilon and L minus epsilon. This will be, sorry, will fall within this range. Then we say that this limit of the f x is L. Okay. Thank you very much. Thanks.